All right, we are on to the last of well, just about the last. We'll see if projectile motion is actually two videos, but this will be the very end of kinematics. We're going to look at 2D motion and projectile motion. All right, so at this point, we've got a lot of tools and motion knowledge under our belt. We've got equations, the big five, along with our basic acceleration, velocity, displacement equations to calculate uh, mathematically or algebraically answers to problems. Now, some of the longer or more in-depth problems that we're going to see are those that involve two-dimensional motion. So, two-dimensional motion is, start with that definition by itself. Where one-dimensional was motion that was only horizontal or vertical, so an object that was traveling purely side to side or purely up and down. Now we're going to have motion that is in both x and y directions simultaneously. So that's our definition here. Motion that is in both x and y directions simultaneously. Can't spell this word. Simultaneously. Here. Whoop. There we go. Simultaneous. Okay, we'll call it good enough. I think that's mostly correct. So many of these two-dimensional motion problems will specifically be projectile motion. And a lot of the problems that AP will give you is projectiles specifically. But we're just going to wait on that for a second because we're going to talk about a basic example of 2D motion where we could separate x and y variables to solve for kinematics values. Because that's a lot of what we're doing is just like back in vectors when we did vector math and we had to add up all the I hats together, all the j hats together, we did the x direction vector addition separate from the y direction vector addition. We're going to do that here because when we use big five equations, those have a lot of vectors in them, and we're going to add or subtract vectors within the big five. So to do that, we have to make sure that we're adding up all the x vectors and adding up all the y vectors separate from each other, which is why up to this point, we've only used x direction big five equations or y direction. So we're going to have to be careful to keep doing that. Okay. But we've already mentioned the importance of that and making sure we don't accidentally put a y direction equation into an x direction or a y direction variable into an x direction equation or something like that. So let's draw an example of 2D motion. This is going to be a general example before we move on to projectiles. So this example of 2D motion. We're going to start with a boat crossing a river. So I'll do some nice little water effects in the river. So here's a river. I don't need it quite that large. We'll make a more modest river. Okay, something like that. Put our nice little waves in there, because why not? All right, this example is a boat crossing the river. All right, let's draw our little boat here. Okay, and this boat is going to have some velocity because it's got either a motor or oars or whatever is causing it. Maybe it's a sailboat, but whatever it is, it's got some way to propel itself or move across the river. So we're going to start off with a velocity here that could be our y direction velocity, because as we see it, we're looking from a bird's eye view above the river, and we see the boat crossing across the river from bank to bank in the y direction. Okay, so it has some velocity. That might stay the same, it might change. We're not doing a full problem here, so we don't have to worry too much about is there acceleration? Do we have to think about initial and final y direction velocity? But it has some velocity. So that could be a value. You could do Vy initial, Vy final. Um, you could look at displacement, right? Because from one bank to the other, there's a displacement delta y as it moves across. There will be some amount of time associated with that. So there's a time to cross. So here's some variables, right? Y direction displacement, Y direction velocity, time. If there's any acceleration, you could throw in the AY as it accelerates and goes faster or slows down as it goes across. So that's all the boat um, variables and physics values. But the river itself also can have some motion to it, and it would because the river is moving and flowing. So let's draw some of those. So the river has a current. We'd have some Vx. Maybe it speeds up or slows down. We're not sure, but as the boat goes across, because of the current flowing downstream or flowing to the right as we see it, the boat's not going to end up exactly across the river from where it started at the tip of that delta y vector. It'll still go through that vertical displacement, that amount of meters from one bank to the other, but by the time it gets there, it might end up somewhere down here because it's drifted downstream with that velocity of the river and ends up at some further point. We could draw the displacement, and there's our delta x. So the boat goes through a displacement not only in the y direction, but also the x direction. And as you can see, right, we're starting to collect some variables for this kind of situation where we could use big five equations and calculate things in both the x and in the y direction. So this is just kind of the basis of two-dimensional motion, is some scenario where an object is moving not only in the vertical direction, but also in the horizontal direction at the same time. And you've got things like y velocity and x velocity, vertical and horizontal displacements to think about. Yeah, and if we think about some of our vector math, even looking at the purple and black arrows for displacement, we probably won't be doing this in a lot of AP problems. They don't really ask you to do this, but you could even do some vector math and add them together using like tip to tail method, or think about those right triangles, right? If the vertical and horizontal displacements are the two components of the total displacement, you could look at that green arrow for the total initial position to final position displacement of the boat. But we don't end up usually needing to do that a whole lot. Instead, we tend to, in two-dimensional problems, we tend to separate out the x and the y variables, right? Everything in black versus everything in purple here on the picture. And then we would deal separately with them in big five equations. There's some crossover like time. The time the boat takes to cross the river vertically as we see it is the same as the time it takes to drift downstream with the current in the x direction. So the time is the common variable we could use for x or y direction equation. And that'll actually be really useful for projectiles as well. Okay, so there's a basic example of 2D motion. Now let's get into projectiles specifically. So, projectile motion. This is a situation where objects are typically launched or thrown from some height above the ground. They could be dropped, but usually they're launched or thrown. Projectile motion occurs when an object which is usually launched or thrown from some height above the ground. My English, with what I put in parentheses, I don't think the sentence is going to make a ton of sense in English, but hopefully I won't get judged too hard for it. So usually launched or thrown from some height above the ground. Now there are some examples. In fact, one of the most classic projectiles um, is actually launched from the ground. So I guess either we could say it's either from the ground or from some height above it. It's not super important like where it's launched from. The main thing is it tends to be launched or thrown, and it follows a parabolic path. You call it arced as well, an arced path until impact. Okay, so we can use all of our kinematics values of velocity, initial velocity, final velocity, displacement, acceleration, time. The one that tends to be least relevant, so we can use um, all motion variables. Although we will find that final velocity is not very often used. We won't see a whole lot of that one. Okay, so um, let's talk about kind of how to approach these. Generally, what we do with projectile motion problems. So when solving these, when solving projectile problems, or really, this also applies to just about any two-dimensional problem we could come up with or deal with. When we're solving these, we must use x or y kinematics values in separate x and y direction big five equations. So this goes back to um, big five equations. This goes back to vectors when we said we want to make sure we're not trying to add together like an I hat and a j hat together. We can add up all the I hat x direction values when we did vector math. We could add up all the j hat y direction ones, but we don't want to mix and match. And even since then, we want to make sure that when we're doing big five equations that we're not putting in um, like a y direction acceleration, a vertical acceleration into our horizontal big five problem or equation. So it becomes very important to keep them separate, right? We do not want to try and say something like the acceleration of gravity in the y direction helps us find the horizontal displacement because it really doesn't end up affecting that. Okay, so we'll kind of go through and we'll mention some of those key values and like how they tend to show up. This will help us also to mention a few things about acceleration specifically, a few kind of key pieces. So we'll start with displacement. It's often a very important value that we see a fair amount in here. So we frequently end up finding horizontal displacement. So we often find either solve for or in some way we're dealing with how far does the object travel horizontally how far it travels horizontally before impact. Now, vertical displacement is also a big one because vertical displacement helps us find specific location called the apex. The vertical displacement is related to the apex. Which is the highest point the object reaches. When we draw some examples later on and we actually visually depict or draw projectile motion, we'll point out that apex or that highest point that the object reaches. So we could say from launch until the object reaches its apex or highest point, there's a vertical displacement there because it starts off launching, it goes upwards, and then it'll travel upwards through a vertical displacement until it gets to that highest spot. So those are a couple things that we tend to see with displacement. Also, one last thing, which we'll see in our examples, is also if our object happens to launches and lands at the same height, then delta y equals 0. So all that means is if we launch an object from ground level, for example, from the ground, and it travels in a parabolic arc through the air, it arcs through the air, hits its apex, comes back down, and then lands. If it lands at the same height it launched from, displacement is the difference between starting and ending position. Remember that displacement doesn't care about the path in between. It doesn't care about what happened in the middle. The only thing displacement measures is the difference between your starting and ending position. And vertically, there is no difference from starting and ending position if you launch from the ground and you land back on the ground. So anything that launches and lands at the same height has a vertical displacement of 0. That's very, very handy for a lot of equations when we're solving with Big Five. Okay, initial velocity. This is a big one for sure. This initial velocity. So this is often an angled initial velocity. It's not always, but frequently our v0 is at an angle just because of how projectiles work, and a lot of the time you're launching it like up and to the right so that it arcs through the air and as a parabolic path and then comes and hits the ground or wherever it impacts. Okay, it just depends how the object is launched or thrown or whatever. When this happens, so often an angled v0, in which case, when that happens, we need to use our trigonometry skills with vectors. So we're going to use our trigonometry skills, to split into its x and y components, which would be Vx initial and Vy initial. Those two are going to be very important because we're going to start a lot of projectile problems with an initial velocity that you're going to maybe be tempted to put that initial velocity right into your Big Five equations. But if it's at an angle, if we're launching at an angle, that velocity will not be a purely x or purely y direction velocity. It will be angled, a mix of both. It'll have some horizontal and some vertical velocity being launched like upwards and to the right, for example. And if we're putting things into Big Five equations, we need to be sure that we are using x or y values like vx initial, vy initial in our appropriate x or y direction big five equations. So we really need that trig, that sine and cosine that we looked at with vectors in the beginning of unit 1, to which we haven't touched in a while, but we're coming back to it now. So we're going to need that to split the vector into its components, find vx initial, vy initial. All right. Then we use those in our separate big five equations for x and y. So this is a really big one, especially when there's an angled initial velocity. We could also mention, we'll mention it with one specific case of projectiles. It's like sometimes there's only a horizontal initial velocity, which kind of makes it easier because then you only have a vx initial and you don't have any vy initial. But we'll look at that in a bit. All right, acceleration. So for projectiles, there's a couple really important things for acceleration. And that is we make some assumptions, or based off of our knowledge. It's not an assumption all around. We have some knowledge of what affects or accelerates our object, but we also make some assumptions about it. So even though air resistance, even though air resistance would slow down our object, even though air resistance would slow down our object in both x and y directions, because air resistance is going to slow down any object that's moving through the air. So if your object starts moving upwards as you launch it up, it's going to slow down. If your object starts moving to the right, then it's going to slow down, because air resistance, if you launch it up, air resistance pushes down on it. If you launch your object to the right, air resistance pushes to the left. It opposes that direction of motion, which we'll look at in Unit 2 with forces a little bit more. And yeah, even though air resistance would slow down the object, in both x and y directions, what we do is we choose to treat that as negligible. The word negligible just means so small that we can ignore it or treat it like it doesn't exist. That's what we do with air resistance. We say, well, there is some amount of slowing down due to air resistance in the x and the y directions, but it's relatively small enough that we can pretend it doesn't exist or treat it as negligible. So why do we do that? Well, we do it because the math with air resistance can be particularly nasty. It's not the worst thing you could ever do, but I've done it a little bit, and it's just really there's a lot of stuff going on with it. It becomes really tricky math-wise to correctly factor in and calculate air resistance and how it affects the velocity, and then your velocity starts affecting your air resistance, and you've got this circle of things that affect each other, and it just becomes a lot to deal with. So we're not going to do any equations that deal with air resistance in that way. We're going to kind of dodge that by saying, hey, let's treat it as negligible. All right, instead, we treat projectile motion as free fall. So we treat projectile motion as free fall. In that case, in free fall, that's where the acceleration values are acceleration in the y direction equal to gravity, because gravity is the main thing affecting the vertical direction. When you throw something upwards or launch it upwards as a projectile, it will slow down due to gravity, because the velocity would be upwards, acceleration of gravity downwards, and it would slow down as it first starts to go up. Your object will reach the apex at some point, at which point then the gravity continues to accelerate downwards, and the velocity starts to pick up faster and faster in the downwards direction, and then your object speeds up due to gravity until it hits the ground. So in the y direction, we were going to use 10 or negative 10. If you're assuming down is negative, then you could do negative 10 meters per second squared. It's just gravity. So equal to g, little g, the acceleration of gravity. Okay. Cool. And then what else here? So a x is actually equal to 0 based on our assumption that there is no air resistance. Because really the thing that would slow down our object horizontally or affect its velocity would be air resistance. But because we chose to treat it as negligible, we can pretend or say that there is no acceleration whatsoever in the x direction, because once we are not taking into account drag or air resistance, then nothing in the x direction would slow down or speed up our object while it is in the air. And that's the key thing about projectiles, right? The launch process, sure, if you're launching it out of a slingshot or a catapult, yeah, something is speeding it up at that point. But as soon as the object has been launched, it is now in the air in free fall, where the only acceleration on it is gravity in the y direction and nothing in the x direction. Okay. Very cool. Last one is time, so we'll look a little bit at that. For time, there's a few key things to point out. The big one we already mentioned with the two-dimensional motion is we can use the time value, whatever time t is, in both x and y big five equations. Because the thing about time when it comes to projectile motion or 2D motion is that whatever is happening as your object moves horizontally and moves vertically, the time it takes for the object to move somewhere horizontally, whatever it's doing side to side, and for the time it takes for the object to move vertically, whatever it's doing in the y direction, those are the same thing, right? The time it takes a projectile to go up and come back down is the exact same time as it takes that projectile to fly horizontally and land somewhere further to the right or to the left. So we can use that time in both the x and the y big five equations. It's actually a really, really useful thing. And the reason we also get away with that is we can't take our vectors like a y and ax, vx initial, vy. Those vectors have x and y subscripts. We can't just put the y acceleration into an x equation. That does not work. But time is a scalar. That's a big part of this reason why we can do this. And we're allowed to put it in both x and y equations because it's a scalar. And as I mentioned, right, the other reason being because the time is the same amount for horizontal motion and vertical motion in this projectile type scenario. All right. Yep. So the time it takes for an object to travel and hit the ground horizontally from launch to landing is the same as the time it takes to travel and hit the ground vertically from launch to landing. Okay, so we're going to draw a example of the classic projectile. So we'll start with the classic one. We'll do a couple variations on it in a little bit here and kind of wrap up with that. And yeah. Okay. So let's do it. This is our classic projectile. And what the classic projectile is means that it's launched at an angle. So a lot of times we'll see that angled launch. And it lands at the same height it was launched from. We referenced that up there with delta y, and we'll point that out again here. Alrighty. So let's draw that projectile. Draw the ground here. I'm going to make it a little bit lower, make sure I give myself plenty of room to draw this. My ground is very bad. I'm going to tap out and use a... Oh, wow. So many options. What I just want... There we go. We're going to drag it down here. My goodness. And we'll make our ground level nice and flat. Excellent. Now let's draw our projectile. So we're going to launch it from the left side. We'll travel over to the right. And we'll do a... We will do an initial velocity like so. Well, maybe a little bit steeper here. Go. Really struggling with drawing straight lines tonight. I don't know what it is. See if I can do a decently straight one. Not the worst. Okay. So we'll start with this. We'll take this angled initial velocity v0. Keep in mind that is a total initial velocity, and we're about to look at the two components of that. We got some angle theta going on here, whatever your angle is, call it theta. And then we're going to draw the two components of this initial velocity. So when you're using big 5 equations, we want to make sure that we're finding Vx initial and Vy initial. Just a quick reminder on trig for vectors. I'm going to make sure I kind of keep this out of the way of what I'm doing next, Vy initial. The fact that we launch upwards, Vy initial, and we launch to the right, Vx initial, we can find those using sine and cosine. So if we remember from vectors, to find the x component Vx initial, we simply take, because this is the adjacent side, there's a right triangle, the red line, the hypotenuse, the purple lines, the two sides of our right triangle. And to find the adjacent side Vx initial right next to our angle here, we're going to take the cosine, because cosine of theta is adjacent over hypotenuse. We're going to take the cosine multiplied by that hypotenuse, which is the total velocity V initial. So if a problem tells you that an object is launched at 10 meters per second at an angle of 30 degrees, you would take cosine 30 times 10 meters per second and find the component of that velocity that is directly to the right. How much velocity does it have to the right initially? And then Vy initial, similarly, that's opposite to the angle theta, so we would use sine here, sine of theta times V initial. And that should get us our two components, Vx initial, Vy initial. Okay, now let's carry on with drawing the projectile and making a few comments about key points of interest in our classic projectile. So we'll see how well I can do with a parabolic path. Really not doing so well tonight. All right, let's see if I'm going to adjust my hand to a different location and see if it helps me out at all. That sure didn't. All right, what if I start at the apex and go from there? Nope. All right, I'm going to see if there's a parabola option. Kind of. Nope. All right. We'll just have to settle for a less than perfect line. That's okay. Forgive my less than stellar arc. although I've seen worse. Okay, so our object is launched, it travels in an arc through the air, and then eventually lands. Okay, so let's point out a few points of interest here, one of them being the apex. At the apex, we can make a couple notes, one being the object in the vertical direction starts off with some velocity vy0. The acceleration of gravity is always acting downwards. We could draw a reminder that our acceleration ay is just gravity. We decided that with air resistance out of the picture, the only thing we're worrying about for acceleration in the y direction is just gravity. 9.8 or 10 meters per second squared downwards. So that's going to slow down the object, right? It starts going upwards, it slows down due to gravity, it gets slower in the y direction, slower, 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 slower. It's going to briefly stop at the apex. So at the apex, our Vy is equal to 0. Then it starts to pick up velocity as it briefly stops, turns around, and starts going down. Now, the acceleration of gravity continuing to act downwards will speed it up faster and faster and faster until it hits the ground. We could also note that when it gets back down here, an interesting thing is that Vy final, even though we don't usually deal with that final velocity a whole lot, it's actually equal to the same amount as Vy initial, but opposite direction. So if we launch it upwards from the ground at 5 meters per second of upwards velocity, it will come down, and just before it hits the ground, that final velocity right before impact would be -5. So if we start at positive 5 meters per second, we'd end at -5. If it starts going up at 7 meters per second, it would be -7. Because we could think about it as it slows down exactly halfway through, it slows down to 0 from the starting velocity, then speeds back up with the same acceleration of gravity as it's had the whole time, same acceleration, speeding it up, reaching the same velocity there that it had at the beginning. Okay. Cool. A couple other things to point out is in this particular example, the time to apex is equal to 1/2 of the total time. So that total time, let's see if we can do a better subscripting job here. So time total, TOT, over 2. If it takes 4 seconds to fly through the whole projectile motion, then it would take 2 seconds to reach the apex. In this classic projectile example, half the time is to get to the apex, the other half the time is to go back to the ground. All right, we also mentioned, along with acceleration, of course, AX equals 0 due to the assumption that there is no air resistance. And then we could draw, as long as we're at it, we could draw our horizontal displacement starting at the beginning. I'm actually going to do a straight line for that one because we'll make it easy on ourselves. No, that is a box. There we go. Okay, we'll draw a straight line like this. We'll throw an arrow on it, and that'll be our displacement. There is our delta x. Often something we solve for, often something important that we deal with in these problems. All right. Oh, I did have an extra line. I guess I'll just get rid of that. Goodbye. All right. So we've looked at initial velocity, being able to split it into components when we launch at an angle for this classic projectile launching and landing on the ground. We've looked at acceleration, which is gravity downwards in the y direction. No x acceleration at all. We've looked at the velocity reaching 0 at the apex. The final velocity will be exactly the same number as the initial in the y direction. We can also note for the horizontal, the final velocity, Vx final, would be exactly the same as Vx initial because it hasn't changed. If there's no acceleration whatsoever, your velocity doesn't change in any way, and your final velocity is the same as your initial. So exact same x velocity the whole time through, which also means something people will often forget. Even though it stops in the y direction, it keeps moving in the x direction. So we still have that same velocity that we could draw as uh, Vx at this point is still exactly the same as Vx initial, the one we started with. So all throughout the entire projectile motion until it hits the ground, the object maintains that same horizontal velocity. And it is still moving to the right at the apex, even though it stops in the vertical direction briefly before coming back down. One last thing to mention is displacement. That would be delta y. And because it launches from the ground, landing on the ground, delta y is equal to 0. The starting height is on the ground. The ending height is on the ground. Even though it went up and then came back down, displacement does not care about the path you took in between. Displacement only factors in or calculates the difference between your starting and ending position. And in the y direction, that is 0. You end in exactly the same y position that you started on the ground. Okay, this is all useful stuff. Now, I am going to box some of this in green because some of these are, we'll add this here, these are specific to the classic projectile. This is one of them. If you don't launch and land at the same height, your final velocity won't be the same number but opposite to your initial. We'll show some variations of projectiles. This is another one that's specific to the classic projectile example. This is another one. Now, some of these are universally true for all projectiles, like the acceleration being gravity in the y direction, x direction is 0. That's true for all projectile motion. Oops. Oh my goodness. We're deleting things I didn't want to delete. I'll just redraw it. Okay. Another thing that is true for all projectiles is that the velocity is 0 at the apex. That's just when it reaches its highest point, its y velocity stops, but any x velocity continues. And of course, if you have an angled launch, all of this is true for any projectile. For any projectile motion, you can find Vx initial, Vy initial using that sine and cosine. But these three in particular, boxed in green, these are only true when we launch and land from the same height for this classic projectile. All right, let's look at a couple variations of that. So these we're not going to go into nearly as much detail. You might see them here and there, but we'll just mention a couple things about them. So variations of projectile motion. We'll look at a few here. First, you might see a problem where an object is launched, rolled, or thrown from some height, but it like rolls off a table or something with an initial velocity that is purely horizontal. So we get this Vx initial. And this is actually a really nice one because we don't have to do any trig. We don't have to do sine and cosine. If it tells you the ball rolls off the table at 4 meters per second, that is the x initial velocity. And when it rolls purely horizontally at the beginning off the table, or is launched horizontally, Vy initial is 0. There is no vertical starting velocity when it is purely horizontally rolled or launched like so. It travels still in an arc of a sort. There's also not really an apex here. I mean, it starts at the apex because the highest point it is at is where it starts, and then it just starts to go down from there. Yeah, there's some vertical displacement, right? There's a delta y that is downwards from the top of the table to the ground. There's also a delta x, how far it lands. Your acceleration values are still the same. Ax is 0, ay is gravity. The time still works for both x and the y direction. So really the main difference here, other than the things circled in green, like this is no longer true. Delta y is no longer 0. The final velocity is not the same number as, but opposite to the initial. And there's really not a time to apex because, again, it kind of starts at the apex. It starts at the highest point and then goes down from there. But you might see that one. It's kind of a fairly common one you can see. We'll also look at one where you launch from above. This one I haven't seen a whole lot of, but it's possible you'd see it. Launch from above and land below, but we do it at an angle. So now you'd go back to trigonometry and you would say with an angled initial velocity, I'm going to use sine and cosine for that to find the x and the y. Initial velocity, we'll do a little arc here as it goes the air and hits the ground. Okay. For this one, we could note that our v y final, whatever it is, will be greater than, or the absolute value of that, absolute value sign, will be greater than, I wrote less than, so let's fix that. Late at night, and I am trying to keep up with this. Okay, so there's that. Less than Vy initial. Okay. So if your object launches and its upwards velocity is 2 meters per second, it's going to be moving much faster, like -5 meters per second when it gets down there, because it's had less time to speed up and less time to slow down to get to the top, and then it's had a lot of time to speed up going all the way down to the ground. And yeah, the time to apex is not half. It would be a short time to reach apex from the launch, and then a longer time from the apex all the way down to the ground below. And there'd still be some delta y, right? For the whole projectile motion, the entire thing, the delta y would just be like the height of the cliff or the height of the table. So from beginning to end, the displacement would be from the top down to the bottom. So we could draw that in there. We may as well throw in the little delta y. We'll put it on the first one too. So we've got a downward displacement like so. There's your delta y. Same thing here. Boom, boom. Delta y. Okay. We'll look at one last example and then we'll call it for this. So the other thing you could see is starting from down below, ending up higher. You also don't see a ton of this. But if it does happen to come up, we'll just mention a couple things about it. This one, you'd see like an angled launch of some kind, an arc or projectile motion, landing up on top. Okay, and what we could identify here is that the final velocity, absolute value of Vy final is now less than absolute value Vy initial. The idea there is that you have to launch it pretty fast upwards so it makes it up on top of this cliff or table or whatever you're launching it up onto. And because we launch it pretty fast, it's got an initial y velocity. It takes a while to slow down, reach the apex, hit zero velocity at the apex, y velocity, I should say. It still has x velocity at the apex. Slow down, reach zero y velocity, but then it only has a little bit of time to pick up velocity in the downwards direction and speed up before it hits. So it's speeding up a little bit, but then before it has time to gather a lot of velocity with the acceleration of gravity in the downwards direction, it just hits the top of the cliff or table or whatever you're launching it up onto. So yeah, you get a lot larger number or absolute value for that initial velocity compared to the final. But those aren't super duper important. They're just things to keep in mind, as well as like time to apex. Here, there's a long time to apex. It reaches the apex, and then it's a little short time until it hits the end and stops its projectile motion. So I think the most common one probably is that first one that we looked at. You might see those other two on occasion, but probably not a whole lot. Okay, we'll do more with projectile motion solving. We'll do some example problems and stuff in class, and we have a whole project around using projectile launchers to try and calculate things with big five equations. But yeah, when we do that sort of thing in class, just a reminder that we're going to use both x and y big five equations. We got all these variables running around: vx initial, vy initial, ay, ax, delta y, delta x. We don't use the final velocities quite as much, but time will definitely be in there as well. So those we're going to make use of by simultaneously. We'll look at like, okay, what can we use our y direction big five equations for? What can we use our x direction big five equations for? And oftentimes we'll do either some substitution or we use the y direction to find something. Actually, a very common one that we'll see pop up is you often use the y direction to solve for time. And then you can take that time value that you got from the y direction and plug it into the x direction to find what you need. So there's sort of like two-step processes um, that can happen. And we'll try to run through. I'll do one more video where I talk a little bit about AP problems and some of those styles of things. And in that video, I'll also kind of do a collective list of kinematics problem solving. So some reminders on graphs and 1D motion and 2D motion and big five equations and all that. So we'll kind of do a summary of going into the AP problems as we work more on them and prepare for a test. Um, what are some just general like strategies, tips, ideas, skills, things to keep in mind? Okay, we'll call it there. So there's 2D motion and projectiles. We'll see you for one more kind of wrap up video in Unit 1, and then we'll be, this is it for like content. There's no new material for Unit 1, and then we'll be getting ready for a test. So thanks for watching. We'll see you in class and see you for the next video.